Hello friends, once again welcome to chemistry classes by Vijay Kumar Sethi in class 12th P block elements. We were discussing about group 15 elements, and in this video we'll discuss about anomalous properties of nitrogen, chemical properties of group 15 elements. In this we will discuss about reactivity towards hydrogen, oxygen, halogens and metals. First, see the anomalous properties of nitrogen. Nitrogen differ from rest of the members of this group due to its small size, high electronegativity, high ionization enthalpy and non-availability of d orbitals. Nitrogen has unique ability to form p-pi multiple bonds with itself and with other elements having small size and high electronegativity, that is carbon and oxygen. Thus, nitrogen exists as a diatomic molecule with a triple bond. Okay, with a triple bond. One is sigma and two are pi bonds. Okay, this is one. It should be sigma and two. These are the pi bonds. Okay, between the two atoms. Consequently, its bond enthalpy is very high. And again, that's why due to the presence of triple bond, nitrogen is less reactive or inert at the room temperature. Catenation tendency is weaker in nitrogen. As we know, what is catenation? Self-linking. Okay. Why this tendency is weaker in nitrogen? Because single nitrogen bond is weaker than the single phosphorus bond. Now, why this nitrogen single bond is weaker? Because of high interelectronic repulsions of the non-bonding electrons owing to the small bond length. Because of small bond length, the non-bonding electrons are close and that's why they repel to each other. That's why nitrogen single bond is weaker. There is absence of d orbitals in its valency shell. It cannot expand its covalency beyond 4. Nitrogen cannot form d-pi-p-pi bond as the heavier elements can form. For example, R3p double bond O and R3p double bond CH2, where R is the alkyl group. Okay. Now let us see reactions of group 15 elements, that is chemical properties. First we will discuss about the reactivity towards hydrogen. All the elements of group 15 form hydrides of the type EH3, where E is the element, nitrogen, phosphorus, arsenic, antimony and bismuth. The stability of hydrides decreases from NH3 to BiS3 due to decrease in bond dissociation enthalpy. Dear students, down the group, size of the atom is increases. That's why bond length is increases. When bond length increases, bond dissociation enthalpy decreases. That's why stability of these hydrides decreases from NH3 to BiS3. BiS3 is the least stable, and that's why their reducing character of the hydrides increases. Stability decreases, reducing character increases. Ammonia is only a mild reducing agent, while BiS3, being most unstable, is the strongest reducing agent amongst all the hydrides of group 15 elements. pH3 is a much weaker base than NH3. Actually, if we compare the basic property of these hydrides, all these hydrides having the lone pair of electron on the central atom. Nitrogen also having lone pair of electron, pH3 also, and all these hydrides also having the lone pair of electrons. And that's why they can accept a proton. Okay, that's why they are base. But if we compare their basic nature, then due to the size of central atom, the NH3 is the stronger base. Okay, because in this case electron density is more compared to the another hydrides. Due to high electronegativity and small size of nitrogen, NH3 exhibits hydrogen bonding. Again, this is the one characteristic feature of NH3 in solid as well as in liquid state. Because of this, it has higher melting and boiling points than that of pH3. Okay. Now, let us see the properties and their increasing or decreasing order. If we see stability, we already discussed. This is NH3 is the most stable and BiS3 is the least stable. This can be seen from this bond dissociation enthalpy decreases down the group. because the bond length, that is EH bond length, is increases down the group. And due to this stability, reducing character is reverse. When stability is least, reducing character is most. Okay. Basic property, as we already discussed, NH3 is highly basic, then PS3, and they having no basic character. If we compare the boiling point and melting point, actually these are the covalent hydrides, and in case of covalent hydrides, the force of attraction is weak van der Waals force, and weak van der Waals force depends on the surface area and size. Larger the size, larger the magnitude of van der Waals force, and more the boiling point and melting point. But exceptionally, if we say, according to this trend, the melting point and boiling point should increase from NH3 to BiS3. But this is NH3 have the exceptionally high melting point and boiling point because of hydrogen bonding. You can say like that's why this is NH3 having the boiling point more than pH3. The same way this NH3 have the higher melting point than PS3 or SbS3 and AHS3. Clear? Reactivity towards oxygen. All these elements form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than that of lower oxidation state. Important point is there. In higher oxidation state, okay, that is more acidic. How can you compare? Higher oxidation state means more positive charge. More positive charge means easily accept the proton. Okay. Higher oxidation state of element is more acidic. Positive charge is there. That's why acidic nature is there. Positive charge is there. It means it can accept electron easily because this is positive. And according to the Lewis concept of acid and base, electron acceptors are acid. That's why oxide in the higher oxidation state are more acidic. Okay. Their acidic character decreases down the group. Oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. That of arsenic and antimony amphoteric, and those of bismuth predominantly basic. That is, from top to bottom, the acidic character is decreases and basic character increases. Okay. Reactivity towards halogens. These elements react to form two series of halides, EX3 and EX5. Nitrogen does not form pentahalide due to non-availability of d orbitals. We already discussed. Pentahalides are more covalent than trihalides. Again, this point is important. Simply, we can generalize that any compound in the higher oxidation state of the same element is more covalent than that of in lower oxidation state. Okay, according to the Fajan's rule, if you remember in class 11 we have discussed, according to the Fajan's rule, more positive charge means more polarizing power. More polarizing power means more covalent character. Clear? That's why we can say this is due to the fact that in pentahalide plus 5 oxidation state exists, while in case of trihalides plus 3 oxidation state exists. Since elements in plus 5 oxidation state will have more polarizing power than in plus 3 oxidation state, the covalent character of bond is more in pentahalides. Okay. All the trihalides of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable because this F is high most electronegative element. Trihalides except BiF3 are predominantly covalent in nature. Reactivity towards metals. All these elements react with metals to form their binary compounds exhibiting -3 oxidation state, such as Ca3N2, calcium nitride, Ca3P2, calcium phosphide, Na3As, sodium arsenide. Okay, students, thank you.